Alright, this is the Thermodynamics 2, School of Mines, well, South Dakota School of Mines. Homework number 2, which is Clapeyron and Gibbs free energy / equilibrium. Problem number 4. Okay. So problem number 4 is a Gibbs problem. Okay. It says salt dissolves in water versus staying as salt. Okay. So I have water and I have salt. It goes in. Well, it's salty. Okay. So, is this process driven entropically, enthalpically, both, or neither? Okay. So I gotta go through my tree. First off, does it happen? When I add salt to water, does it dissolve? Otherwise, you got some freaky salt. Yes, it happens. And I ask myself about entropy. Okay, so again, entropy is chaos. But it's also, amount of microstates, amount of possibilities, amount of configurations. Okay, and I got to think about phase 2. Okay, so in this first picture, I have salt. I have salt, which is a solid and liquid, and then I just have liquid. Is that entropically favorable? Yep. Yeah, I mean everything is in a liquid state, so to speak. Okay, so that's entropically favorable. I also got to think about mixing. Okay, mixing is always entropically favorable. Okay, here, am I mixed or am I mixed here? Or am I mixed in neither or am I mixed in both? Yeah, I'm only mixed in here. So is it more entropically favorable to be mixed? To be dissolved? Yeah, because I'm mixed here and I'm not mixed here. So that's also entropically favorable. Well, that's really all to think about. So this is definitely an entropically favorable process. Okay, so it definitely goes up. Okay. But it still doesn't tell me what drives it. Could be entropy. It also could be enthalpy. So I need to ask about enthalpy too. Okay. And again, when I'm asking about enthalpy, I'm asking about interactions. Are the interactions more favorable here or here? Okay. And I got to think about things as a whole. You want average. Now, and yeah, sometimes I have to make some assumptions, and so there is ambiguity in these sometimes, okay? And I'm okay with you arguing the ambiguity. That's what makes you good scientists and engineers. But, there are some assumptions that need to be made, okay? Really, the assumption to be made here is I'm not pouring in a bucket of salt into a glass of water. I am pouring a dash of salt into a... So, in terms of magnitudes of interactions, there's a lot more water interactions than there are salt interactions. Okay. And so, yes, I'm going here, but on the molecular level, I'm going from, my salt crystal, which has pluses and minuses, okay, and water, which has, hydrogen bonding, to water molecules interacting with salt ions. And still hydrogen bonding. Yeah, minus, plus, you get the point. Okay. So, are the interactions better? Well, what is the main interaction that's going on here? Okay, first off, is there hydrogen bonding? Well, there is. There is hydrogen bonding. There's hydrogen bonding between waters. But there's hydrogen bonding between waters either way. And I know in some other problems we talked about, other molecules in here breaking up the hydrogen bonding network. Okay, so maybe but like I said, there's a concentration issue here. So for the most part, there still is just as much hydrogen bonding. So that's pretty much constant. Okay. There's also ionic interactions between the salt. But, there's still ionic interactions between the salt. But what is new? there's ionic interactions between the salt and the water. Well, yeah, there's ionic interactions between the salt and the water. So, which law dictates interactions between salt and water? Which law dictates electrostatic interactions? That's right, Coulomb's law. You know, it says Q1 times Q2 over some stuff. Okay? One of them being, you know, distance. It's either distance or distance squared. I always get them mixed up. But we'll just say it's distance. Maybe it's either an energy or a force, but close enough for government to work. Alright, and so, you know, the charge on salt is either +1 or -1, and the charge on water, well, the oxygen is about minus, you know, 0.84, and the hydrogen is about, you know, positive 0.42. So in terms of Coulomb's law, what's better, negative 0.84 times 0.42, or negative 0.84 times +1? Yeah, the 0.84 times +1. The ionic interactions are so much better. Okay, and so water loves ions. It loves salt. Okay, hence why there's so much in the ocean. But I mean, water really does love salt. It would rather interact with salt than itself because of those electrostatics. Okay. So, in terms of enthalpy, okay, enthalpy goes down, which means, you know, the interactions are better, which means this is driven by both. Okay. It's driven by entropy because of the mixing, and, you know, I don't have a solid phase anymore, but it's also driven by enthalpy because the interactions just as a whole are better.